So why do we use oxidation states? It helps us to keep track of the transfer of electrons. Okay? We need to know something about the charge before and after, so we can know whether 2 electrons were transferred or 3, and often more importantly, whether they were gained or lost. Okay? Now, we've done a lot of work with monoatomic ions so far. Mono meaning one atom, okay, with a charge. If you have something like sodium chloride, okay, we can easily analyze the 2 pieces. We know that the sodium piece is 1 plus and the Cl minus, the Cl is 1 minus, okay? And we can do predictions from before and after with this, okay? But we're going to start moving into oxidation states, which we need for molecules. If we have something like water, that's a molecule. There's no charges to any of that atoms, okay? This is way back to Chem 20 bonding. This is what water would look like. It has shared electrons. There's no charges whatsoever. Oxidation numbers and oxidation states gives us a system to deal with these molecules that have shared electrons. So what is an oxidation state? Okay, it is a positive or negative number. And notice I didn't say charge, okay, because it's not a charge. It's either a plus or minus number assigned to an atom under an assumption. We're going to assume that there's no shared electrons. Okay? We're going to take those shared ones and push them to an atom. Okay? Now, to show that this is just an oxidation state, not a charge, we write the order the other way. Okay? So for charges, it's the number first followed by the sign. For oxidation states, you put the sign first and the number second. Okay? No, I'm not too picky with this. When you're back in class and you do a quiz and you do it the other way, I'll give you feedback, but I'm not going to take marks off. Okay? But the textbook, hopefully you will eventually learn and consistently do it the proper sequence depending on charge or numbers. So most importantly, how on earth do we come up with these numbers? Okay? How do we get oxidation states? Okay? Just before I get there, I want to emphasize that these aren't charges. They're not real, but they let us track electrons. Okay? So we're not making up electrons. We're just taking 2 shared electrons and pushing one to one atom, one to the other to track it being electrons. So let's use a nice small molecule that's a bit easy to visualize, methane. Methane is a molecule with no charges, a carbon in the middle, and a pair of electrons out to each of the H's. Okay. Now what oxidation numbers do is take those shared electrons and push them to the more electronegative atom. Pushes all the electrons to the atom that has the greatest attraction. Now between carbon and hydrogen, okay, now electronegativity goes back to Chem 20, you're not going to be using it again, but it's the numbers above the atoms in your periodic table. Okay, so carbon is 2.6. Okay, hydrogen you can't see on the camera, but it's 2.2. Carbon has a greater attraction for electrons. So we're going to take all of these shared electrons and count them on the carbon. Okay. We're going to pretend, and I emphasize the word pretend, they're not shared. And then we're going to figure out what would the charges be if there was no sharing. We'll start with hydrogen. Okay. This hydrogen has 1 proton, and when we push all the electrons to the carbon, it has 0 electrons. Okay. So I'm going to have to figure out the charge based on 1 proton and 0 electrons. There's a question, why do we pretend they're on the carbon? We pretend they're on the more electronegative atom. We're taking the shared electrons and pushing them to the atom that has the greatest pull. Okay? Okay. You'd find the electrons are slightly closer to the carbon anyway, and we're going to count them all on the carbon. You know, there's going to be lots of shortcuts for this, so what I'm doing is the theory, but I'll give you all the shortcuts shortly. Okay. So that hydrogen, when we count all the electrons on the carbon, there's one proton, there's no electrons, so it's going to be 1+. Okay, you would have a charge of +1. Just going to separate that out a little bit. Okay. And all those outside H's would also be 1+. They have one proton and no electrons. This carbon in the middle, if I just count valence electrons, there originally were 4 valence electrons on carbon, and we've now pushed 8 electrons to it. Okay? So it had 4 originally, but there's now 8. Okay? We've pushed 4 extra electrons to it, which gives it a charge of -4, or an oxidation number of -4. Even I wrote that backwards by mistake. So the middle is -4, the outside is +1, +1, +1, +1, +4 in total. If you add up all the oxidation numbers, they add up to the charge of the original molecule, which was 0. Okay, so those are the oxidation numbers for the hydrogen and carbon. Okay. Now that's the theory of what we're going to do, but it's going to be way simpler. We're not going to have to look at oxidation numbers and push electrons around. I'm going to talk about all the trends you need to know. There's a lot of atoms or ions that always have the same oxidation number. So we're going to run through oxidation numbers you need to know. Alberta Ed, Chem 30 is written where students memorize these. So the first category that Chem 20s need to just memorize is the oxidation number of atoms in their elements or elemental form. Within the way this course is set up, all the oxidation numbers but one are going to come from the trends in this table, and we're going to figure out the one missing oxidation number. In post-secondary, it can get a lot more challenging. So atoms in their elemental form, or atoms in elements, this is when you have just one type of element. So maybe you have Cl2, okay, just chlorine, it's a diatomic, or just oxygen, okay, or a metal, maybe you have just copper, or just zinc, okay. That's what I mean by atoms in their elemental form, okay. Hydrogen gas, maybe. Okay. Anytime you have just one type of atom in its elemental form, its oxidation number will always be 0. Okay. The second category we're going to deal with is hydrogen, and then we'll move on to oxygen. They show up a lot, and they have nice repeating patterns that really help us. Okay. Hydrogen, in compounds, so that would be something like hydrogen with at least one other element. So hydrogen with oxygen would be water, maybe HCl, hydrochloric acid, or something a little more complicated, a sugar, C6H12O6. Okay. As long as the hydrogen is in something with at least one other type of element, it's going to have an oxidation number of +1. Okay. So it wasn't a coincidence or that we got +1 up above with methane. You know it's going to be +1 because hydrogen was paired up with carbon. Okay. Now there's one other slight variation of this. It doesn't come up very often. I never really test you on this, but if you have hydrogen plus a metal, okay, hydrogen paired up with something with a very low electronegativity, then hydrogen ends up with the higher electronegativity, and it flops from +1 to -1. Okay. So if you had lithium paired with hydrogen, lithium hydride, okay, the lithium would be +1 and the hydrogen would be -1. Then I switch to blue. Probably will never see this, but it's something I have to teach you. Oxygen, we have the same type of split. We have most of the time, and then we have one exception. Okay, hydrogen in compounds. So that would be like, well, water would work again. That's oxygen in paired with another element. Okay. Or that same sugar, C6H12O6. Okay, we know the hydrogens are all going to be +1. The oxygens are going to be all -2. That's the most common oxidation state. Its oxygen is virtually always -1 unless it's in a peroxide. Okay? Peroxides are when you have two O's bonded together. Not like we saw in a carboxylic acid, but in, we're going to use hydrogen peroxide for a lab. H to an O to an O to an H. Okay. I never try to trick you with these and hide the peroxide. It'd be right in a question. You know, the reactant is hydrogen peroxide or some other type of peroxide. In this case, the oxidation number is only -1 instead of -2. Okay. Again, you will see peroxides in this course, so I left it red. The blue line is the one that you're not going to see tested from me. The last row, which is something we've really already dealt with, monoatomic ions. So one atom in an ion. Okay. So that would be something like magnesium 2+, or maybe you have Fe3+, or Cl-. The oxidation number is just the charge. Okay. And again, we've already looked at that. But it's one of those trends you need to be aware of, and it's going to show up. So what's left is I'm going to go through, I've got about 5 examples prepared, and then I have some practice for you to do, and that wraps up this lesson on oxidation states. Your next lesson, lesson 5 tomorrow, we'll use this in some applications to balance some more complex reactions than the ones we've been looking at so far. We've finished organic chemistry, so it's you should be able to decode ethanol. So F is 2 carbons. OL means we have an alcohol. Now you can just write molecular formulas and figure out oxidation numbers from just the formula. It's a little harder, so I'm going to draw it out first. Okay. And I want to find the oxidation number of all of the atoms. The first thing I and you are going to do is sort of think through the table we just looked at and assign all the oxidation numbers we can based on this table. So atoms and elements, hydrogen, oxygen, and monoatomic ions. Well, I see hydrogen and oxygen that we should be able to do. Hydrogen in a compound, okay, it's not hydrogen by itself, or to be 0, it's hydrogen in a compound is always 1+ as an oxidation state. So there were 6 different hydrogens that I'm labeling 1+. Okay. Charged first, so it's an oxidation state. I see oxygen in a compound. Okay, that's clearly not a peroxide. We don't have 2 O's back to back. So that's 2-. Okay. And I'm left with 2 carbons that I'm going to have to figure out. I'm going to have to figure out what is the oxidation state of carbons. Okay, I'm going to take out those question marks so I can put numbers in once I figure it out. Okay. Now, what you haven't been taught yet that I'm about to show you to figure out that one missing atom is the fact that the oxidation, the sum of the oxidation states always equals the charge. Okay. Now this could be the charge of, we could have an ion or we could have a molecule. Okay. This works for both. Okay. If that's a little confusing, you need to see an example. Okay. So I'm going to break this down. We're going to look at all the cations plus all the anions, all the positive oxidation states plus all the negative oxidation states are going to have to equal our charge. Okay. We have ethanol. What is the charge overall of ethanol, of this molecule? The question is, the answer is simple. It might seem confusing. It's a very small number. Yeah, it is 0. All molecules, if the charge isn't written in, it is 0. We don't write in 0 charges. But if you have water, you have ethanol, any of our organic molecules, they're all neutral. Okay? So the sum of our oxidation numbers have to add up to 0. Okay? So I'm going to figure out all the positives, all the negatives, and whatever's missing to make this 0 must be our carbon. So what do we have for cations or positive oxidation states? Just the hydrogen. We got +1, +2, +3, +4, +5, +6. Okay. No other positives yet. For negatives, we only have one O, and that's -2. Okay. And we've got to add something for the carbons to make this 0. So +6, -2, what do we need? We don't have enough negatives. Okay. We got +6, we only have -2. How many more minuses do we need to get those charges to balance? Yeah, we need 4 more. We need -4. +6, -2, -4, that would sum up to 0. So the oxidation states of the carbons must add up to -4. But we have 2 of them. We need -4, but there's 2 carbons, so they must be -2 each. This one must be -2, and this one is -2. Okay? Now, if you add up all those red oxidation states, they all sum to 0. Okay? And this is the game we're going to keep playing in this unit. Figure out all the oxidation states, but one with memory or memorization, and figure out the missing one. Okay? So that's ethanol, a neutral molecule. We're going to do the same thing with dichromate, that's an ion. Cr2O7, and the whole thing has a -2 charge. That black -2 isn't for the oxygen, that's the whole thing. So our cations plus our anions have to sum to the charge. Okay. I'm using a bit of short form. I went C+ for cations, A- for anions equals the charge. And in this example, the charge is 2-. Okay, so we're going to have a little bit of integers to sort of play with. First step is go to your table and write out any oxidation states that table tells us. Okay. And we don't have any monoatomic ions. We've got 9 different atoms in this ion, so it's not a monoatomic ion. We've got no hydrogen. We do have oxygen. Oxygen's in a compound. That's always 2-. Okay. Now we have to realize there's 7 O's, and every one of them is 2-. Okay. So there's -14 in total if we sum them all up together. Chromium, we don't know. Okay. We don't have any rule for metals in compounds. So we're going to have to figure that out. So we only have 2 different, we've got chromium and we've got oxygen. The oxygen is minus, so we have -2 times 7 of them. So that's -14. We have no positives. Our chromium must be our positive piece. Okay. And now is where we kind of have that integer part. What's in that blue circle? What, when we combine with minus 14, gives us minus 2. Okay. Well, if the blue circle was 14, we'd get 0. It's not 14. Do we have to add 2 or subtract 2? Let's check. Plus 12 minus 14, and you could throw this in your calculator, and you do get minus 2. Okay, we just have wrote it 2 minus. So plus 12 works. That is the sum of all the positive oxidation numbers. We've got 2 chromium again, so that plus 12 has to be split over our 2 chromium. So we don't have a question mark there anymore. We have plus 6. Each chromium is plus 6. The 2 of them together is plus 12. And we've solved all our 2 oxidation numbers, plus 6 and minus 2. Oh, I did mess up. Just that oxygen is written the wrong way around. It's an oxidation number, so I needed to put the charge first. Okay. That's 2 examples. I'll do 3 more, and we'll wrap up Thursday. So I've handwritten them out already. We've got sodium carbonate, ammonium chloride, and calcium dihydride. Or no, sorry, just calcium hydride. So first, these first 2 are a bit confusing. I haven't done any examples of ionic compounds. Okay. So we've got sodium carbonate. In our heads, we kind of have to think of this as sodium plus and CO3 2 minus. Okay? You don't have to actually write it out separate, but you have to realize sodium carbonate is ionic. We've got 2 ions, a cation and an anion, and that helps us realize that that sodium is plus 1. Okay? Because that's just it's based off a monoatomic ion. Okay? So when you have ionic compounds, in your head, think of each ion pieces separate. Okay? If you have a monoatomic ion within an ionic compound, you just use its charge. Okay? Now we do have to remember that there's 2 sodiums there. They're each plus 1. Okay? Our carbonate, there's not much else. That's not a monoatomic ion, so I can't do a lot with it. What I can do is we've got oxygen in a compound, so that's going to be minus 2. Now I'm at the point where I know sodium is plus 1. I know oxygen is always minus 2. Okay? Carbonate is not a peroxide. You don't see the word peroxide in its name. Okay? All of those O's are bonded to the C. Okay? If you don't see the word peroxide, don't go looking for it. Okay? The only thing missing is that carbon. Okay? We can figure that out. Cations plus anions is going to equal the charge. Okay? I'm going to do this for the whole thing. Sodium carbonate formula units have no charge. Okay? The sodium has a charge, the carbonate has a charge. When you put it all together, they cancel each other out. Okay? The 2 sodiums and the 1 carbonate. What do we have for cations? We have just sodium, and there's 2 of them. So plus 1 each, so plus 2 in total. For the anions, we just have oxygen. There's 3 of them, so 3 times minus 2, or minus 2, minus 4, minus 6 for all 3 of them. Now we have to figure out which side is low and bring it up to the other number. 2 is the low side. So I need some more positives to get this to sum to 0. I need 4 more. Plus 2, plus 4, and minus 6. They all sum to 0. So my missing oxidation number for carbon is plus 4. Okay. Carbon varies. Depending on the question, you will see different oxidation numbers for carbon. Okay? Not for oxygen, not for hydrogen. Okay? So that's an ionic compound where you kind of have to think of the pieces separate and then do the whole thing together. We have to use the same strategy with ammonium chloride. Okay? We've kind of got to think of it as an ionic compound and see if there's any monoatomic ions, which there is, and then sort of go back and deal with the whole thing. Okay? So NH4Cl, it's ionic, ammonium, and chloride. We've got a monoatomic ion with the chloride. Chloride is 1-, so we have a -1 oxidation number. Okay. Then I can kind of let go or forget about the fact that it's a monatomic ion and just start solving for one missing atom. We've got hydrogen in a compound. Well, that's always +1. We're left with nitrogen, as there's no rule to figure out nitrogen. It varies. We are going to have to do the cation plus anion equals the charge. And for any ionic compound, the whole thing is 0. Positive charges, we just have hydrogen. There's 4 of them. They're each +1. So 4 times 1 +4. Minus, we only have our Cl. There's 1 of them. -1. That's got to add to 0. My low side that I have to bring up is the negative side. I don't have enough negatives. I need 3 more of them to get this. +4 and -1 and -3 adds to 0. So that's my oxidation state for nitrogen. Last example, the rules kind of give us both numbers. We've got calcium hydride. This is the one rare time where hydrogen is paired with a metal. When you see hydrogen paired with a metal, it's not +1, it's -1. Okay? Now that makes sense. We've got, we end up with 2 ions here. We've got a metal and a non-metal. Calcium will be a monoatomic ion, 2+. And it makes sense for hydrogen to be 1-. Okay? That causes all the oxidation numbers here to add up to 0. Okay? We've got 2+, 2 hydrogen and -1, 2-, and that's what causes the sum to 0. Okay? Again, we don't write all ionic compounds have charges of 0. All of these ionic compounds on this slide have 0 charges, not written in. There are 2 ions that have charges, but they net to 0. So this is a lesson that leads into tomorrow's lesson, balancing redox reactions where there's a whole bunch of molecules. Okay? Particularly leads into a lot of biological examples. If you've done Bio 20, Bio 30, you've studied things like the Krebs cycle, cellular respiration. All of those are redox processes. They're all electrochem processes with an exchange of electrons, and we'll go through a lot of those. And this material would come up again in biochemistry in university if that's in your future.